Roughly 85% of all matter in the universe is completely invisible. It doesn't glow, it doesn't reflect light, it doesn't show up on any instrument we've ever built, and yet it outweighs everything you can see. Every star, every planet, every galaxy by a factor of 5 to 1. Scientists have spent decades and billions of dollars trying to figure out what it actually is. So today we're breaking down every single theory about dark matter and what the evidence says, starting with the one that almost everyone believed was the answer: WIMPs. WIMPs, or weakly interacting massive particles, have been the heavyweight champion of dark matter theories since the 1980s. The idea is simple. There's a particle out there with a mass somewhere between 10 gigaelectron volts and several teraelectron volts that barely interacts with normal matter. And when I say barely, I mean billions of them are passing through your body every single second and you feel absolutely nothing. Zero. Not a tingle. Yet collectively, these particles outweigh every visible star in the entire universe combined. So naturally, physicists built enormous underground detectors to catch them. Experiments like Xenon 1T, LOX, and Super CDMS operate deep underground and at incredibly cold temperatures, all to detect the faintest collision between a WIMP and a regular atom. The Large Hadron Collider has been smashing particles together since 2008, looking for evidence of WIMPs from the other direction. And after over 15 years of dedicated searching, the result is nothing. Literally zero confirmed detections. This has created what physicists are now calling the WIMP crisis. Some argue the entire model should be scrapped. Others insist we just need bigger, more sensitive detectors, which is, not ideal when you've already spent billions, but WIMPs are just the beginning, because if the universe's favorite candidate can't prove it exists, the alternatives start getting a lot weirder. Axions. If WIMPs are the heavyweight boxer of dark matter candidates, axions are the opposite. We're talking particles so absurdly light they make electrons look like bowling balls. A single axion could weigh somewhere between a billionth and a trillionth of an electron's mass, depending on the model. And yet, what they lack in size, they more than make up for in sheer volume. If axions exist, the sun's core alone could be pumping out staggering numbers of them every single second. While you're sleeping, while you're doing literally anything, a fire hose of invisible particles could be blasting through you and you wouldn't feel a thing. Here's the thing though, axions weren't even invented to explain dark matter. They were first proposed back in 1977 to solve a completely unrelated headache in physics called the strong CP problem, which is basically the mystery of why the strong nuclear force respects asymmetry it has zero obvious reason to respect. Physicists needed a fix, came up with axions, and then realized these things would also perfectly explain all the missing mass in the universe. Two problems, one particle. That's either the most elegant solution in modern physics or the most suspicious coincidence, depending on who you ask. Skeptics argue that a particle solving everything conveniently is a red flag, not a feature. If your answer works for every question, maybe it's not actually answering any of them. The Axion dark matter experiment has been hunting these things since the mid-1990s. 3 decades of searching with zero confirmed detection. But momentum is building. Axions are no longer the underdog. They're the rising challenger to WIMP's throne. And unlike WIMPs, they haven't spent decades disappointing everyone. But axions and WIMPs at least have one thing in common. They're both exotic. The next candidate is something far more ordinary, and that's exactly what makes it interesting. Massive compact halo objects. MACHOs are the common sense answer to dark matter. What if it's not some exotic particle we've never seen before? What if it's just stuff that's too dim to detect? Brown dwarfs, neutron stars, rogue black holes drifting through galactic halos, completely invisible unless you know exactly where to look. Normal matter are matter, just dark. And honestly, that's a really satisfying explanation. No new physics required. No hypothetical particles. Just objects we already know exist, hanging out in the cosmic suburbs where nobody thought to check. The name itself is basically a flex. MACHOs, the massive astrophysical compact halo objects, was coined specifically as a rival to WIMPs. Two camps of physicists literally named their theories to fight each other. Science is beautiful. The idea got serious traction in the early 1990s, and teams were actually testing it with dedicated surveys. The EROS, OGL, and MACO experiments spent years staring at millions of stars in the Large Magellanic Cloud, watching for gravitational microlensing events. That's when a massive unseen object passes between us and a distant star, bending the light and temporarily brightening it just enough to detect. Millions of stars, years of continuous observation, real telescopes, real data, real results. And they found some. That's the thing, MACHOs are real. They exist. The MACHO project detected several microlensing events, suggesting these objects could account for a meaningful but limited fraction of the galactic halo's mass. somewhere around 20% at most, but 20% isn't 100%. It's not even close. And follow-up results from Eros actually drove that number even lower. MACOS could explain a slice of the mystery, but the rest, something else entirely. The common sense answer was almost right, which in physics basically means completely wrong, almost. Because one specific type of macho refused to stay dead, primordial black holes. If machos were the sensible older brother who showed up to dinner in a polo shirt, primordial black holes are the one who kicked the door down, set the table on fire, and somehow got a standing ovation for it. The idea is beautifully simple. In the first fraction of a second after the Big Bang, the universe wasn't smooth. It had density fluctuations. Tiny regions where matter was packed just a little too tightly. Some of those regions collapsed directly into black holes. No dying star required, no supernova, just raw physics doing its thing before the universe even had atoms. Here's where it gets wild. The predicted mass range spans from objects lighter than a grain of sand to monsters thousands of times heavier than our sun. That's not a range. That's a suggestion box with zero rules. For decades, this theory sat in the interesting but whatever pile. Then 2015 happened. LIGO detected gravitational waves from two black holes merging, and the entire physics community said, wait, what if those were primordial? Because the masses were heavier than what stellar evolution models comfortably predicted. They were in a suspicious range. That single detection blew the doors open. Depending on mass window and distribution, primordial black holes could account for a meaningful fraction of dark matter, though observational constraints have ruled out many mass ranges. Microlensing surveys have found candidate events that keep the debate very much alive. The argument now is whether this is the boring answer or the revolutionary one. Some physicists hate it because it means dark matter isn't some exotic new particle. It's just collapsed stuff we already understand. Others argue that's exactly what makes it elegant. And the best part, gravitational waves mean we can actually detect these things smashing into each other. One of the few dark matter candidates with a detection method already producing real data. But if invisible black holes sound strange, wait until someone suggests we just throw out gravity entirely and rewrite the laws of physics from scratch. Modified Newtonian dynamics. Every theory we've covered so far starts from the same assumption. There's invisible stuff out there we can't find. But what if that assumption is completely wrong? What if there's no dark matter at all? And the real problem is that we got gravity wrong. That's exactly what physicist Mordechai Milgram proposed in 1983. Instead of inventing an entirely new form of matter, he suggested something way more audacious. He said Newton's laws of gravity, the ones we've trusted for over 300 years, stop working correctly when gravitational acceleration drops below a specific threshold. Below that number, gravity behaves differently than predicted. Stronger, specifically. And here's the thing, it works. MOND successfully explains the rotation curves of over 150 observed galaxies without a single particle of dark matter. Zero. No invisible halos, no exotic matter, no billion-dollar detectors buried underground. You plug in the formula, you get the right answer. It even makes predictions that differ from standard dark matter models, predictions that have held up under observation. For a theory that basically says Newton was slightly off, that's genuinely impressive. But before you throw out every dark matter textbook, there's a problem. Actually, several. MOND works beautifully at the scale of individual galaxies, but the moment you zoom out to galaxy clusters, it falls apart. It can't explain the cosmic microwave background without bolting on additional modifications. Its relativistic extension, called Teba's theory, adds so much complexity that critics argue you've just traded one mystery for a messier one. And Teba's took a serious hit when gravitational wave observations contradicted certain versions of it entirely. The physics community leans heavily against MOND, though it has a dedicated minority who call it elegant and predictive. Mainstream astrophysicists call it a parlor trick that only works at one scale. The debates get genuinely heated, which is rare for a field where people normally communicate through equations. But whether you love MOND or hate it, at least it's only tweaking gravity. The next theory tweaks dark matter itself, and the results are somehow even weirder. Self-interacting dark matter. So-called dark matter, the standard model everyone's been working with for decades, is really good at explaining the big picture. Large-scale structure of the universe, nailed it. Cosmic microwave background, perfect fit. But zoom into individual galaxies, and it starts getting things wrong. Specifically, consistently, documentably wrong. The standard model predicts dark matter should pile up into dense, spiky cores at the centers of galaxies. What we actually observe? Smooth, spread out cores. It also predicts way more dwarf galaxies orbiting the Milky Way than we can find. These aren't minor discrepancies. These are the model looking you in the eye and confidently giving you the wrong answer, repeatedly in the same places. In 2000, David Spergel and Paul Steinhardt proposed a fix. What if dark matter particles don't just ignore each other completely? What if they occasionally bump into one another? We're talking roughly one collision per particle per 10 billion years. That's like two people living in the same city for the entire age of the universe and bumping into each other exactly once at the grocery store. But at cosmic scales, even that tiny interaction rate redistributes dark matter away from those problematic dense cores. The predicted cross sections are around 0.1 to 10 square centimeters per gram, giving physicists actual numbers to test. And in 2006, the Bullet cluster delivered. Two galaxy clusters smashed into each other, and astronomers could literally watch the dark matter pass through itself while normal matter got stuck in the middle. The separation was visible. The interaction rate was constrainable. Real upper limits on dark matter self-interaction, measured from an actual cosmic collision. That's what makes this theory interesting. It's not reinventing the wheel. It's a patch update. It takes the existing framework, acknowledges the specific bugs, and adds one small mechanic to fix them. Whether that's elegant or just duct tape depends on who you ask. But if self-interacting dark matter is the pragmatic fix, the next theory takes things in a completely different direction, one where dark matter isn't even a particle at all. Sterile neutrinos. Regular neutrinos are already the most antisocial particles in existence. Trillions of them pass through your body every second without touching a single atom. They're basically ghosts, so naturally, physicists looked at that and said, what if there's an even more antisocial version? Enter sterile neutrinos. These things interact with normal matter in literally zero ways except through gravity. That's it. No weak nuclear force, no electromagnetic force, nothing. Regular neutrinos at least occasionally bump into something if you wait long enough. Sterile neutrinos won't even do that. They're the ghost within the ghost, the introvert's introvert, the particle that left the group chat before the group chat existed. And here's why they're actually a reasonable candidate. Neutrinos already exist. We know they come in three flavors. Sterile neutrinos would just be a fourth type that happens to be heavier and even more reclusive. Their predicted mass sits somewhere in the 1 to 50 kiloelectron-volt range, which makes them roughly 10 to 500 times heavier than regular neutrinos, but still incredibly tiny. In the early universe, they could have been produced through a process called oscillation, where regular neutrinos occasionally convert into their sterile cousins. Enough of that happening in the first fraction of a second after the Big Bang, and you've got yourself a universe full of invisible mass. The problem is finding them. The IceCube Observatory, buried deep in Antarctic ice, has been searching for signs of them. X-ray telescopes like Chandra and XMM Newton have scanned galaxy clusters looking for a specific emission line that sterile neutrinos should produce when they decay. The results so far? Nothing confirmed. There were some tantalizing anomalies from the Mini Boone experiment that hinted at extra neutrino types and got people excited for a while. But those results are controversial at best and inconclusive at worst. Supporters will tell you we simply haven't searched the right energy ranges yet, which is either hopeful or delusional depending on who you ask. But if you think a particle that refuses to interact with anything sounds speculative, wait until you hear about dark matter that isn't even particles at all. Fuzzy dark matter. This one has the best name on the entire list, and it's not even close. Fuzzy dark matter. Sounds like something a physicist named after their cat. But the actual concept behind it is one of the most genuinely mind-bending ideas in modern cosmology. Here's the setup. Proposed around 2000 by physicist Wayne Hu and others, and seriously developed further in the years since. Fuzzy dark matter suggests that dark matter isn't made of heavy particles bumping into things. Instead, it's composed of ultralight bosons with masses around 10 to the negative 22 electron volts. For context, that's so light it makes a regular neutrino look like a bowling ball. And because these particles are so absurdly light, quantum mechanics kicks in at cosmic scales, which normally doesn't happen. Quantum effects are supposed to stay tiny, stay in their lane, stay at the subatomic level, but fuzzy dark matter says no. The de Broglie wavelength of these particles stretches across entire galaxies. Dark matter stops behaving like individual particles bouncing around and instead acts as a wave-like quantum condensate, simultaneously a particle and a field stretching across galactic scales, which is, completely normal and not at all terrifying to think about. But here's where it gets interesting beyond just sounding cool. Numerical simulations show that fuzzy dark matter could actually explain the internal structure of dwarf galaxies, something conventional cold dark matter has consistently struggled with. Standard models predict dense, cuspy cores in dwarf galaxies. Observations show smooth, spread out cores. Fuzzy dark matter's wave behavior naturally produces exactly those smooth cores without any additional tweaking. That's a real testable prediction, not just math on a whiteboard. There's a generational divide happening over this one too. Younger physicists tend to gravitate toward it because the mathematics are elegant and the predictions are specific. The older guard sometimes dismisses it as beautiful speculation without enough experimental grounding. Basically, the physics equivalent of "that's a nice theory, kid. Now show me the data." Fair enough. But if fuzzy dark matter sounds strange, wait until you hear the theory that says dark matter and dark energy are secretly the same thing. Dark fluid. What if dark matter and dark energy aren't two separate mysteries? What if they're the same thing? That's the pitch behind dark fluid theory. And honestly, it's one of the most philosophically beautiful ideas on this entire list. The concept emerged in the 2000s, and it asks a question so simple it's almost embarrassing that nobody asked it sooner. We've got dark matter making up about 27% of the universe. We've got dark energy making up about 68%. Together, that's 95% of everything that exists. And we understand 0% of either one. So what if they're actually the same substance, just behaving differently under different conditions? Think of it like water. Water can be a solid, a liquid, or a gas depending on temperature and pressure. Same stuff, wildly different behavior. Dark fluid theory proposes something similar. One unified substance fills the cosmos, but its properties change depending on where it is and what's around it. In dense regions like galaxy clusters, it acts like dark matter, pulling things together. In the vast empty stretches between galaxies, it acts like dark energy, pushing everything apart. The idea is that a single exotic equation of state could reproduce both attractive and repulsive gravitational effects, which basically means one substance with the mathematical flexibility to switch personalities depending on the neighborhood. Data from WMAP and later the Planck satellite could theoretically constrain what this fluid looks like, narrowing down its properties based on how the cosmic microwave background behaves. But here's where it gets complicated. Critics argue that dark fluid doesn't actually explain anything. It just takes two labels we don't understand and replaces them with one label we don't understand, which is, not ideal. The theory is elegant on paper, but thin on predictions you can actually test. And in physics, elegance without evidence is just poetry. But if you think renaming the problem is bold, wait until you hear about the theory that says dark matter is literally an invisible jello filling all of space. Scalar field dark matter. Imagine the entire universe is filled with invisible jello. Not chunks floating around, not jello particles bouncing off each other. One continuous, smooth, impossibly massive block of jello stretching across everything, and you can't see it, touch it, or taste it. That's scalar field dark matter. And yes, it sounds ridiculous, but the math checks out, which is either reassuring or terrifying depending on how much you trust math. This theory proposes that dark matter isn't made of individual particles in the traditional sense. Instead, it's a coherent quantum field made of ultra-light spin-zero bosons called scalars. These bosons are so light and so numerous that they stop behaving like discrete particles entirely, and instead form a single smooth classical field, kind of like a Bose-Einstein condensate, except this one is massive and invisible and everywhere. Now, if you're thinking, wait, that sounds exactly like fuzzy dark matter, you're not wrong. Fuzzy dark matter is essentially a specific subset of this, but the emphasis differs. Fuzzy dark matter highlights wave-like behavior at galactic scales. Scalar field theory cares more about the field itself, its potential, its self-interactions, and how it slots into broader physics framework. It's the difference between describing ocean waves and describing the ocean. Here's where it gets interesting. String theory predicts an absolute abundance of light scalar particles, like embarrassingly many. So if string theory is even partially correct, ultra-light scalar fields fill in the universe would almost be expected. The de Broglie wavelengths involved can reach kiloparsec scales, comparable to entire dwarf galaxies. Simulations suggest this would suppress small-scale structure formation and leave specific fingerprints in gravitational lensing patterns. But here's the problem. Many of those predictions overlap significantly with other dark matter models, even if we found exactly what scalar field models predict. Distinguishing it from competitors would be extremely difficult. No dedicated experiments exist. No detector is being built for it. It lives almost entirely on paper, beloved by string theorists, largely ignored by experimentalists. But if the next section's theory taught us anything, it's that sometimes the universe kills your favorite idea with actual evidence. Red hot dark matter. This one's quick because the universe didn't even have to think about it. Hot dark matter was a serious contender back in the 1980s and into the 1990s, built around particles we already knew existed. Neutrinos. The idea was simple. What if dark matter was made of lightweight particles moving at relativistic speeds, significant fractions of the speed of light, tiny particles absolutely screaming through space instead of gently clumping together? Sounds cool. Here's the problem. If dark matter particles are moving that fast, they can't settle down long enough to form small-scale structure. They'd smooth everything out, erasing density fluctuations on galaxy-sized scales through a process called free streaming. Think of it like a long-exposure photograph. You leave the shutter open too long and everything blurs into nothing. No sharp edges, no defined shapes. Just a cosmic smear. And that's exactly the opposite of what we see. The universe is full of sharp, defined structure. Galaxies, clusters, filaments, walls of matter stretching hundreds of millions of light years. The cosmos is lumpy, extremely lumpy. Hot dark matter predicts a top-down formation scenario where superclusters form first and galaxies come later. And that's simply not what happened. Surveys from SDSS, 2D-FGRS, and the Planck mission all confirm this. The cosmic microwave background and large-scale structure observations ruled out hot dark matter as the dominant component. Neutrinos contribute a tiny fraction at best, so it's dead. Cleanly, definitively dead. And honestly, that's kind of refreshing. Not every theory on this list gets a dramatic unresolved ending. Sometimes a theory makes a clear prediction, the universe says absolutely not, and everyone moves on. That's science actually working the way it's supposed to. But if you think ruled out theories are strange, wait until you hear about the one that says dark matter is literally just normal matter from a parallel universe, the mirror universe. This is the one that breaks your brain. The idea of mirror matter has roots going back decades. But physicists like Zurab Barajani have been major champions of it as a dark matter candidate. The concept sounds like it belongs in a Netflix sci-fi series, not a physics paper. There's a parallel hidden sector of reality sitting right on top of ours, containing mirror particles that have all the same properties as standard particles, but with flipped parity. Mirror protons, mirror neutrons, mirror atoms forming mirror molecules, forming mirror structures. An entire shadow cosmos, overlapping with ours like two transparencies stacked on an overhead projector. And dark matter, that's just their normal matter, a mirror sector's worth of stuff, and we've been feeling it press against ours through gravity this entire time without knowing it. Let that sit for a second. The theory actually has roots in parity symmetry restoration, which is the annoying part. It's not just some guy rambling on a forum. Mirror baryons would interact with our matter through gravity and potentially through very feeble kinetic mixing with ordinary photons, meaning this shadow twin could theoretically form its own stars, planets, maybe even structures we'd never detect because they barely talk to us at all. You could be sitting inside a mirror star system, right? You'd never know. It would just feel like, well, gravity. Here's the thing though. While there have been some experimental efforts looking for neutron to mirror neutron oscillations, the theory still lacks the kind of unique confirmed observational signature that would distinguish it cleanly from other dark matter models. It shows up constantly in popular science articles and has a dedicated but relatively small community in the actual dark matter literature. It's the theory equivalent of a really compelling movie pitch that nobody's figured out how to film yet. But that's also kind of the point. We started this video with WIMPs, particles so numerous trillions pass through your body every second. We ended here with the possibility that an entire mirror sector's gravity is what's been warping our galaxies. 12 theories, 12 completely different answers to the same question. And the honest truth is we still can't see the thing we know is there. We can feel it pulling. We just can't name it yet. The search continues. If you enjoyed this video and want to see more, click the video on the screen now.